Hi, this is lesson 5 in our course Electromagnetism, and in this lesson, we're going to discuss about the RL, LC, and the LRC circuit. On to our discussion on the different kinds of circuits, let's first discuss your self-inductance or simply the inductance. Any circuit that carries a varying current has an EMF inducing it by the variation in its own magnetic field. Again, any circuit that carries a varying current has an EMF inducing it by the variation in its own magnetic field. By Lenz's law, a self-induced EMF always opposes the change in the current that caused the EMF and so tends to make it more difficult for variations in current to occur. So if in your circuit you have a varying current I, your your circuit will have an induced EMF where this induced EMF opposes the change in the current that is caused by your varying current. And so if you have this EMF, this self-induced EMF, there will be a more difficulty in changing the current in your circuit. Self-induced EMFs can occur in any circuit since there is always some magnetic flux through the closed loop of a current carrying circuit. But the effect is greatly enhanced if the circuit includes a coil with N turns of wire, such as this one here. So this one is a coil with some N turns of wire, and as a result of the current, there is an average magnetic flux, EB, through each of the turn of the coil. Now, if the current I in the coil is changing, the changing flux through the coil induces this EMF, which we have talked about earlier. We define the self-inductance here with represented by the letter L of the circuit as shown. So your self-inductance L is equal to N, which is your number of turns, times the magnetic flux B divided by the varying current I. So this is how you're going to get for the self-inductance L of your circuit. The self-inductance is called simply as the inductance, and the SI unit of your self-inductance is the Henry. The SI unit of inductance, called the Henry, is named after Joseph Henry, the American scientist who discovered electromagnetic induction, along with another discoverer who independently also discovered your electromagnetic induction, who is Michael Faraday. 1 Henry is equal to 1 Weber per ampere, or this is equal to 1 volt times second per ampere, or it's also equal to 1 ohm second, or 1 joule per ampere squared. Just as the farad is rather a large unit of capacitance, the Henry is rather a large unit of your inductance. So if you're going to buy inductors in electronic shops, you cannot buy an inductance of 1 Henry because that is too big of inductance. So you can buy inductance of micro Henrys or Henrys and so on and so forth. Just like how you're going to buy picofarads, microfarads for your capacitors. So this person here is Joseph Henry, one of the independent discoverers of electromagnetic induction. If the current I in the circuit changes, so does the flux Pb, and from rearranging this equation here, which is the equation for your self-inductance or inductance, and taking the derivative with respect to time of your of your of both sides of the equation, the rates of change are related by the following. So we have N times the time derivative of your magnetic flux is equal to L times the time derivative of your current I. And from Faraday's law, for a coil with N turns, the self-induced EMF, which is your epsilon, is equal to your negative of N dpb over dt. So this one here, this is just equal to your negative epsilon, or the negative induced EMF. So we have this one again, and again from Pardy's law for a coil with N turns, the self-induced is equal to this one here, and it follows that your epsilon is equal to uh, the negative of L di over dt. This one here is the self-induced EMF in your circuit with varying current. The minus sign in the equation is a reflection of your Lenz's law, and it says that the self-induced EMF in a circuit opposes any change in the current in that circuit, as we have talked earlier. So your induced EMF opposes sudden changes in your current within your circuit. So that's why here you have your negative sign. Some application of your inductors in power transmission and lightning strikes. If lightning strikes part of an electrical power transmission system, like say for example this one here, it causes a sudden spike in voltage that can damage the components of the system as well as anything connected to the system. For example, your home appliances. To minimize these effects, large inductors are incorporated into the transmission system. This uses the principle that an inductor opposes and suppresses any rapid changes in the current. So your appliances are safe when there is lightning, because in your transmission line you have your inductors which opposes or suppresses any rapid change in your current. Now let's talk about your inductors. Inductors are circuit devices that are used or that are designed to have a particular inductance. Your inductors are also called a choke. So either you call this one as your inductor or your chokes. The usual circuit symbol for an inductor is this one here. So you have uh, some curl, which is what we're going to use later when we're going to incorporate now your inductors in your circuit. Of course, you know your circuit symbol for your resistors and for your capacitors. If you see this one here, this represents your inductors. These are different types of inductors, which you can see or which you can buy in electronic shops. And this one here, this is a toroidal inductor. These are inductors which you usually see in in your appliances, okay, and so on. Inductors again always opposes change. For example, in the recurrent circuits, inductors maintain steady current flow even if your supply varies. In alternating current circuits, inductor suppresses or filters frequencies that are too fast. So it depends on what type of circuit you have. Your uh, the role of your inductor there also changes. Now, the potential across an inductor depends on the rate of change of the current through it. As you can see here from the equation, your induced EMF or your potential epsilon is equal to the negative of L times di over dt. Your epsilon depends on this rate of change here, which is your di over dt. Self-induced EMF does not oppose current, but does oppose the change in current. Again, this is important to take note that your self-induced EMF does not oppose your current, but does oppose change in the current. If you can remember, your circuit component that opposes the current is what you call your resistor. And it's different with your inductor because your inductor opposes the change in the current. If I doesn't change in time, the EMF of the conductor is equal to 0. So um, let's say for example, you have a steady current in your circuit here. There's no EMF here in your conductor because your di over dt here of a constant current I is equal to 0. The potential across a resistor drops in the direction of current flow. If you can remember, your uh, your your potential across your resistor, which is your VAB, is equal to the current I times your resistance R. And this is greater than zero uh, if A is at higher potential than your V, then you have your potential difference VA minus VB, which is greater than zero. On the other hand, the potential across an inductor depends on the rate of change of the current through it. Again, the potential across an inductor depends on the rate of change of the current through it. So there's a dependence on the change of the current of uh, of your potential in your inductor. There is no change again if the current is constant, and if you have increasing current in your circuit, you have your potential VA is greater than your potential BV, and if you have a decreasing current, then you have your VA that's less than to VB. So again, if there's no change in current in your circuit, let's say for example, just have a constant I here, your dI over dt is equal to zero, then your L times zero is equal to zero, thus the potential across your inductor here is equal to zero. The MF of the inductor is zero. If you have an increasing current, so if there's an increasing current here, your dI over dt is greater than zero, thus your potential is also greater than zero. The EMF of the inductor here uh, is against the flow of your current. As you can see here, if your current flows here and then your current is increasing, the induced EMF opposes the change in increasing current. So since it opposes, it flows in the opposite direction. And that is, this EMF here is also a positive one. Your inductor actually acts like a temporary voltage storage or a temporary voltage source which opposes or which is opposite to change. And again, uh, this implies that the inductor looks like a battery pointing the other way. If you have this increasing current here, what happens is that since your inductor opposes the change, it seems that your inductor is actually pushing your current back to the other side. So you can imply that your inductor looks like a battery pointing the other way so that the current or the electrons is pushed back towards the left side of your circuit. And note here that your point A is a higher potential than your point B. Now, what if the current is decreasing? If the current is decreasing, then your dI over dt is less than zero. This is just from your calculus. If you have a decreasing current, then that means um, your rate of change of your current is less than zero. And if that is the case, then your induced EMF or your potential at points between points A and B, which is L times d over dt, is also less than zero. So it's a negative. So you still have the same result. The inductor still acts like a temporary voltage source, but this time it points towards the opposite to the change. And now what happens is that the inductor pushes the current in the original direction. So just imagine if this current flow here is decreasing, what the inductor wants to do is that the flow of this current here should be steady. So it adds a little push to your current flow because it does not want that this current here will decrease. So it acts like a battery in the same direction with uh, your current flow. Uh, is in the same direction or is oriented like this because again, it wants, or your inductor wants, that the flow of your current will be steady, so it adds a little push in your current flow. You can just imagine if, let's say for example, you are walking behind your classmate, and then your classmate is suddenly walking slower than his speed at earlier times. So what you usually do so that the walking speed of your classmate is maintained is you push your classmate from behind. So that is the same concept here. And again, note here that this time your potential A is less than your potential at point B. Some relevant concepts. An inductor is just another circuit element like a source of EMF, a resistor, or a capacitor. One key difference is that when an inductor is included in a circuit, all the voltages, currents, and capacitor charges are in general functions of time, not constants as they have been in most of our previous circuit analysis. So again, all the voltages, the currents, and capacitance are in general functions of time. But using your Kirchhoff's rules or your Kirchhoff's rules are still valid. When the voltages and currents vary with time, Kirchhoff's rules hold at each instant of your time t.